In this lesson, we will try to solve another problem using recursion, and the problem is that given two positive numbers x and n, we want to calculate x to the power n, and x to the power n is nothing but n times x multiplied to itself. So there are n x's, let's say, in this expression, and to calculate x to the power n, we perform, if we simply keep on multiplying with x all the time, exactly n minus 1 multiplications. And if we want to write a program to calculate x to the power n, the simplest thing that comes to our mind is that we can start with a variable. Say we want to start with a variable result, initialize it to 1, and then we can simply run a loop from 1 to n and keep multiplying result with x. So result becomes result into x. In this case, you are performing n multiplications because you are initiating the variable to 1 instead of x, but it also takes care of the condition when n is equal to 0, and as we know, x to the power 0 or any number to the power 0 is 1. And as we can see, for an input n, we are running the loop, we are running just one loop n times. So it should be pretty evident that the time taken here in this particular case would be proportional to n, or we can also say that the time complexity of this algorithm would be order of n. Now Albert and Pinto are two students of my code school, and they have been given the assignment to calculate x to the power n using recursion. So once again, Albert and Pinto come up with two different solutions, and let us see what their solutions are. To solve a problem using recursion, we first need to define a recurrence relation or a recursive definition. So Albert says that, hey, x to the power n can be written as x into x to the power n minus 1, and this is true for all n greater than 0. For n is equal to 0, x to the power 0 is simply equal to 1. So x to the power n being equal to x into x to the power n minus 1 is a recurrence relation, because x to the power n is expressed in the form of x to the power n minus 1, and this second condition is our base condition. So let us see what Albert's implementation is. Albert writes a function power that takes two arguments, x and n, and we are only writing pseudocode here, and the function goes like, if n is 0, then simply return 1, else return x into, and we make a recursive call here to calculate x to the power n minus 1. So we pass arguments x and n minus 1, and this is Albert's implementation, and this will work fine for all n greater than or equal to 0. So using this algorithm, if you want to calculate, say, x to the power 8, we make a recursive call to first calculate x to the power 7, and then x to the power 7 goes on to make a recursive call to calculate x to the power 6, and we keep on making recursive calls till x to the power 0, and x to the power 0 simply returns 1, and at this stage the recursion terminates. Now let us see Pinto's solution, and Pinto is a little smarter. He says that x to the power n can be written as x to the power n by 2 into x to the power n by 2 if n is an even number, and x to the power n is equal to x into x to the power n minus 1 if n is odd, and x to the power n is equal to 1 for the simple case or the base case of n is equal to 0. So we kind of have two different recurrence relations for two different cases, and let us see how the program looks like. So Pinto also writes a method power that takes two arguments x and n, and his program also goes like, if n is 0, then return 1, else if n is even, and we can also say if n modulo 2 is 0, then first calculate x to the power n by 2 and store it in a variable. So let's say we have a variable y in which we store x to the power n by 2 by making a recursive call to calculate x to the power n by 2. So this is a recursive call, and we return y into y. Now instead of writing these two statements here, we could also have simply written that return power x comma n by 2 into power x comma n by 2, but that would have been very bad, because in that case we would make two different calls to calculate the same value, which will be unnecessary redundancy. So if we would want to calculate x to the power 8, we will make two calls to calculate x to the power 4 and then multiply them. So we make just one call and store it and then simply multiply it to calculate the square. And finally, if n is odd, which will be our final condition, then we simply return x into x to the power n minus 1. And this also works fine for all n greater than or equal to 0. So now when we want to calculate x to the power 8, then we make a call to x to the power 4. So instead of reducing this to x to the power 7, we reduce the problem to calculate x to the power 4. And further, x to the power 4 recursively makes a call to calculate x to the power 2, and then we go on like to x to the power 1 and x to the power 0. So while Albert's program goes kind of 9 steps here in this structure called the recursion tree, Pinto's program only goes 5 steps in this recursion tree. And if we analyze the recurrence relation of these two algorithms, then Albert's algorithm, the time taken by it is proportional to n, or it is big O of n, or order of n in terms of time complexity. And Pinto's program is order of log of n in terms of time complexity. How Albert's program is order of n algorithm and how Pinto's program is order of log n algorithm is something that we will explain in another lesson. We will try to deduce it mathematically, but as we can see that Pinto's program, which is order of log n, is a lot more efficient than Albert's program. Now couple of things here. When we are trying to calculate exponents, then in a real program, an integer variable which is stored in 32 bits is able to store a decimal number of only 9 to 10 digits, while x to the power n can be really large. So let's, for the sake of algorithmic understanding, assume that we have a machine where all this storage and calculations, arithmetical calculations, is not a problem. So this was exponentiation. In another lesson we will try to solve a very similar problem, modular exponentiation, and we will also mathematically deduce the time complexity of these recursive algorithms. So thanks for watching.